Welcome back to another episode of Data Dive, where we explore the intricate world of databases and data management. Today, we're diving into a fundamental topic that's crucial for understanding how large-scale systems operate: partitioning. You might have come across terms like shards, regions, or tablets in various database contexts, but for our discussion today, we'll focus on partitioning. So grab your headphones as we break down what partitioning is, why it's vital for scalability, and how it impacts query performance. Let's start with the basics. Partitioning is all about dividing a large dataset into smaller, more manageable pieces called partitions. Each piece of data, whether it's a record, row, or document, belongs to exactly one partition. You can think of each partition as a mini database. This structure allows for efficient data management and retrieval, especially in shared nothing clusters where different partitions can be distributed across multiple nodes. This design not only enhances scalability, but also improves query throughput, allowing multiple nodes to handle requests at the same time. Now, why do we even partition data in the first place? The main reason is scalability. When you're dealing with a massive dataset, it's simply impractical for a single node to manage all the data and queries. By distributing partitions across different nodes, you can effectively scale out your system. For instance, if you have 10 nodes, they can ideally manage 10 times the data and throughput of just one node. This means that as your data grows, you can add more nodes to your cluster, which enhances performance. However, achieving an even distribution of data across partitions isn't always a walk in the park. Sometimes, one partition might end up with a disproportionate amount of data or queries, creating a bottleneck, which we call a hotspot. Imagine if you partition data based on timestamps. All recent writes might funnel into the same partition, overloading it while others sit idle. To tackle this issue, various strategies can help balance the load, like hashing keys to ensure that data is spread evenly across partitions. There are several strategies for partitioning data, and one common method is range-based partitioning. In this approach, each partition is assigned a continuous range of keys. This can make range queries efficient, but it can also lead to uneven data distribution if not managed carefully. Another method is hash-based partitioning, where a hash function determines which partition a record belongs to. This helps distribute data uniformly, but it complicates range queries because adjacent keys might end up in different partitions. Cassandra offers an interesting hybrid approach. It uses a compound primary key where only the first part is hashed for partitioning, while the rest of the key is sorted within the partition. This allows for efficient range queries on the sorted data, providing a nice balance between performance and manageability. As your system evolves, you might find the need to add or remove nodes, and that's where rebalancing comes into play. Rebalancing ensures that data is redistributed evenly across the available nodes, helping maintain performance levels as your dataset grows or shrinks. It's a crucial aspect of managing partitions effectively, and database administrators need to keep it in mind regularly. Even with the best partitioning strategies, you can still encounter skewed workloads. For example, if a particular key receives an overwhelming amount of traffic, like a viral social media post, it can overwhelm a single partition. To mitigate this, you might implement techniques such as adding random numbers to the keys to spread the load across multiple partitions. However, this introduces complexity to your read operations, as you'll need to aggregate data from multiple keys. It's important to recognize that partitioning comes with its own set of trade-offs. While it enhances scalability and performance, it can complicate data retrieval, especially for range queries. In some systems, like MongoDB with hash-based sharding, range queries can become inefficient since they may require querying all partitions. This makes it essential to understand your application's specific needs when choosing a partitioning strategy. Looking to the future, there's potential for advancements in how databases handle partitioning and rebalancing. Ideally, future systems might automatically detect and compensate for skewed workloads, reducing the manual overhead for database administrators. But for now, it's crucial to think through the implications of your partitioning choices and how they align with your application's requirements. To wrap up, partitioning is a foundational concept in database management that enables scalability, improves performance, and helps manage large datasets. By understanding the various strategies and their implications, you can make informed decisions that will benefit your applications in the long run. Whether you're dealing with transactional workloads or analytics, mastering partitioning is key to optimizing your data systems. Thanks for tuning in to this episode of Data Dive. If you found this discussion helpful, don't forget to subscribe and share it with your fellow data enthusiasts. Until next time, keep exploring the fascinating world of data.